Last week in class we began discussing how to balance equations, with the caveat that redox reactions are more complicated than many of the ones that you can do by inspection. The reaction you'll be doing in lab this week, the reaction oxalate with permanganate to determine the amount of oxalate in your compound, is an example of one of these more complicated redox reactions. What is tricky about this is the charge needs to be balanced. You cannot lose electrons in a reaction either. There are two ways to approach these problems. You may have seen the half reaction method in high school. If you're comfortable with the half reaction method and remember how to do it, feel free to balance the equation that way. Today I'm going to show you a different way of balancing redox reactions called the echo method. E is for electrons, C for charge, H for hydrogens, O for oxygens. To balance electrons, you need to know something called oxidation numbers. We aren't going to have time today to go through a thorough explanation of them. Basically, they're another way of counting electron custody. In this system, the oxidation number of oxygen is always -2, of hydrogen is always +1, and other atoms are determined by their charge and by their combination with these other atoms. So if you have an atom or element or ion, the oxidation number is the same as the charge. So for example, the oxidation state of manganese 2+ is +2. And permanganate, MnO4, there are 4 oxygens that each have a count of -2. The ion altogether has to equal its charge, -1. And manganese is some unknown number. We can do a little bit of algebra to figure out that the oxidation state of manganese and permanganate is +7. We can do the same thing with the carbons in CO2. Each oxygen is -2, so the value for the oxygen part is -4. For that to equal the charge on the entire molecule of 0, the carbon must be +4. And oxalate, we have a similar situation as in the permanganate. We have 4 oxygens, so that's -8. The total charge has to be -2. So the 2 carbons have to make up the other 6, so each carbon is +3. We will spend more time on determining oxidation numbers later in the semester. Next, let's look at what happened to the values for the oxidation numbers during this reaction. We had 2 carbons that each went from +3 to +4. If they went from +3 to +4, that means they each lost 1 electron. So we have a net change of electrons lost of -2. In contrast, the manganese went from +7 to +2. So 1 manganese gained 5 electrons. We need the number of electrons lost and gained to be the same. The easiest way to do this is to cross multiply. So to get the same number, we have 2 carbons that each lost 1, so that was 2 electrons lost, and we had 5 gained. The easiest way to rectify that is to cross multiply. So if we have 5 oxalates with 2 carbons each losing 1, we have 10 electrons lost. To balance that, we need 2 manganese atoms gaining 5 electrons, so we have 10e gained. We then put those numbers in to the appropriate places. So we need 5 oxalates, 2 permanganates. Notice we need 4 CO2s because each oxalate generates 2 CO2s and 2 manganese ions. That takes care of the electrons. So 10 electrons lost, 10 electrons gained. The next part of our scheme is looking at the charge. So let's make a little table summarizing what's happening with the charge. So if we looked at the reactants, we have a proton value, which right now we don't have anything in that blank, so we'll just call that whatever hydrogen is. That's what we're going to change to make them balance out. We have 5 oxalates that are each -2, and 2 manganese ions, which are each -1. On the other side, there's no charge on CO2. We have 2 manganese that are each +2, and water has no charge. So we have +4 on the product side, and on the reactant side we currently have 10, -10, plus -2, we have -12, not counting what goes in this hydrogen blank. To make these two values the same, I need to find a value that I can add to -12 to get to +4. That value is going to be +16. So that tells us we need 16 hydrogens. Next, let's balance hydrogens. On the reactant side, we have 16 hydrogens, with the only source being the protons. On the product side, we have waters. There's no other hydrogens in here. If we have 16 on the reactant side, we need 8 on the product side. That gives us 16 hydrogens on both sides. Now if we did everything right, the oxygens should check out. So on the reactant side, we have 20 oxygens from oxalate, plus another 8 from the permanganate, for a total of 28 oxygens on the reactant side. On the product side, we have 8 from CO2, 4 groups of 2, 8 from water. What did I miss? Oh, I had the wrong number in front of CO2. If I have 5 times 2, that means I made 10 CO2s. This is why you do the check. It lets us check out and catch our errors. That means instead of 8 oxygens from CO2, I have 20 oxygens from CO2, and my oxygens balance. Now, it is always a good idea to make a little table for yourself of each atom. Notice none of the species stayed unchanged during the reaction. So this is our final double check, make sure it all worked. So we have 16 hydrogens on this side, 16 on the other from the water. Carbons, 5 times 2 is 10, 10 times 1 is 10. That's the other way I would have caught my error. Oxygens, we have 20 plus 8. And on the product side, we have 20 plus 8 equals 28. Manganese, 2 and 2. And let's check charge. Plus 16 minus 10 is plus 6. Minus 2 is plus 4. And on the product side, we have 2 times plus 2 is plus 4. So our balanced equation is 16 H plus 5 oxalate plus 2 permanganate goes to 10 CO2 plus 2 manganese, or manganate, plus 8 water.